Okay, in this, our third lecture, we're going to talk about the limits of sequences, and sequences will be a basic tool in this course. I'm going to start off with a definition. I'm going to say let L be a number, and suppose that A sub n is a sequence of numbers. And here we have the curved brackets around the AN. It wouldn't hurt you to think of this as an infinity tuple. It often is. More often we think of it an infinitely long list of numbers. Okay. Now we say that L is a limit of the sequence AN if for every epsilon greater than 0 there is an n such that whenever n is greater than or equal to capital N, it follows that the absolute value of n minus L is less than epsilon. So when you think of the absolute value of AN minus L, think this is the distance between AN and L. Okay, and so what this is saying is that we can make the distance between AN and this limit L as close together as we like, provided we go far enough out in the sequence. Okay, so a basic theorem here, and it's a theorem, but we call it a lemma. We call it a lemma because it gets used a lot. Okay, let U be a real number, and let AN be a sequence of real numbers such that A1 is less than or equal to A2 is less than, etc., etc. And they're all less than U. So basically, U is an upper bound for the set of values of my sequence. Okay. Then the sequence AN converges to the least upper bound of its set of values. So if the sequence is bounded above, it will converge to its least upper bound. So let's look at the proof here. Okay, so this proof will provide a basic pattern on how we prove that sequences converge to a given limit. Okay, let epsilon greater than 0 be given. So this epsilon, it's a fixed number, but it's a number that's unknown to us. So we have a mysterious positive number. We have to show that we can make our sequence closer to its target value than that number. Okay. Now let's assume that this number U is the least upper bound of the AI. Okay, so we've chosen just to keep from coming up with new letters all the time. I've used the U and say it's the least upper bound. Okay. Now, so we were challenged with the epsilon. Now we have to find an n that will let us get closer. So choose n to be large enough so that A sub n, A sub capital N, is between U minus epsilon and U. Okay, so how do we know there is such a thing? Well, one, U being a least upper bound is an upper bound, so it's bigger than all of my AN. And if I can't get it within, make my A sub n bigger than U minus epsilon, then U minus epsilon is an upper bound of my AN. And so it's smaller than my U. So yeah, if U is my least upper bound, I can get as close underneath it as I want to. Okay. Now suppose that now that little n is bigger than capital N. So we're going to test and see if this n works. Okay. So then A sub n is less than A sub little n is less than U. Okay. That this is because the elements of the sequences get bigger each time. That's what we stated in the theorem. It follows, okay, that this a sub n must be closer to u than epsilon, because it's getting my a sub little n is up between my a sub capital N and my u, okay. And so therefore a sub n converges to u. So we got it in what? 1, 2, 3, 4, 5, 6 sentences, something like that, and even leaving out a period here in a typo. So 3 parts to this. Challenge with your epsilon, find a capital N that will do the work for you, and then in the third part you're testing to make sure that your capital N works for you. This is the basic 3 parts. Okay, so with this slide we come to another basic tool. I mean, this is something that will be used all the time. It's called the Squeeze Lemma. And suppose that we have a couple of sequences. So one of them is an AN sequence, one of them is a BN sequence, and it's set up so that AN is always at least as big as BN, which is always at least as big as 0 for every natural number n. Okay. Now, suppose that AN converges to 0. Well, then BN must converge too. And so AN is squeezing BN down to 0. And this is frequently used when AN is something we got a good solid handle on, and BN we're kind of fuzzy about, but we do know that AN is bigger than BN. Okay. So let's go through the proof here. So AN and BN are stated in the lemma. Let epsilon greater than 0 be given. Again, the first of 3 parts. We're challenged with an epsilon, which is mysterious and possibly very small. Since AN converges to 0, there is a capital N, so that the absolute value of AN is less than epsilon whenever n is greater than or equal to capital N. And the absolute value here is superfluous. We don't need it. I'm just kind of trying to adhere to form because we could be considering AN minus 0 in absolute value, okay, to make it fit the form of the definition. All right. Now, challenged epsilon, we've chosen capital N. Now, note that little n is greater than or equal to capital N. That when little n is greater than or equal to capital N, the absolute value of Bn is equal to B, because B is a positive number. But because of our hypothesis, our Bn is less than or equal to An, which is equal to the absolute value of An, which is less than epsilon. Okay. Now, so so that absolute value of Bn is less than epsilon for large n, therefore my sequence Bn converges to 0. Okay, so again, we have another named property here. This is the Archimedean property. I'm putting names on these things. You will be required to not only know what these things say, but to know the names that are associated with them. Okay, so what is the Archimedean property? Let epsilon greater than 0 be given. Suppose that m is a number. There is a natural number, little n, such that little n times epsilon is greater than capital M. Okay, so what we're doing here, we're thinking of m, capital M, as being big. It's something big. We're thinking of epsilon as being something small. So think of m is being as tall as a skyscraper. Say the Empire State Building is famous. Say the epsilon is thin like a piece of paper. This is saying if you get enough pieces of paper together, you can stack them up to be taller than the Empire State Building. Okay. Now to prove this, we will proceed by contradiction. Okay. Suppose there is an m such that n times epsilon is never any bigger than this m. This is the big champion m. By the least upper bound property, there will be a number L that is the least upper bound of the set of all products n times epsilon for which that are less than m. So this, all right, so we've got a least upper bound for this set of numbers. Now what does that do? Well, there is a natural number, capital N, so that N minus, so that L minus epsilon is less than N times epsilon is less than L. All right, again, L is the least upper bound, and if we can't get within epsilon of it below, we have a new least upper bound. So we have to get a number in here. So consider the following. Okay, if I take n plus 1 times epsilon, okay, it's equal to n times epsilon plus epsilon. All right, the L minus epsilon is less than the n times epsilon. Okay, so I just replace the n times epsilon with L, and it just gets maybe a little smaller. I add epsilon to it. It's just sitting there, and that gives me L. This means my n plus 1 times epsilon is bigger than L, but wait a minute, L was the least upper bound of all such things. Okay, and so we have a contradiction here. So at this point, we have a lot of examples. Well, not a lot of examples. We have things about sequences. We've got the squeeze theorem. We've got the one where it converges to its least upper bound. We've got this Archimedean property of the real numbers. But we haven't proven a single sequence converges to anything. So what we're going to do now is we're going to prove that the sequence of numbers 1 over n converges to 0. Okay, this is not a surprise to you. This is, but you know, it is something that needs to be proven. Okay, and we're going to go through the same 3 parts. Challenge with an epsilon, find an n, show that the n works. Okay, let epsilon greater than 0 be given. By the Archimedean property of real numbers, there is a capital N such that capital N times epsilon is greater than 1. Now, suppose that little n is bigger than capital N. Then little n times epsilon is bigger than capital N times epsilon is bigger than 1. I can divide both sides of this by little n, and that gives me that 1 over n is less than epsilon. But 1 over n is a positive number, and so it's its own absolute value. So I've got this absolute value of 1 over n is less than epsilon. Therefore, my 1 over n converges to 0 because it's given any small number. If I go far out enough, 1 over n will be less than that small number. Okay, now we're going to prove something that's kind of odd, maybe, and it's interesting, but it will also be useful at various points. And this is that for every open interval from A, B, where A is less than B, every open interval contains a rational number and an irrational number. Okay, both rational and irrationals. You know, it's called the density of the rationals, and often the irrationals get left out. But it's the density of the rationals that sort of surprises people for some reason. Anyway, let's prove this. Okay, as A is less than B, it follows that B minus A is greater than 0. We're cool there. Okay. Now, by the Archimedean property of the real numbers, there is an m such that m times b minus a is greater than 3. That is, m times b minus m times a is greater than 3. Okay. Since m times b and m times a are more than 3 integral units apart, there must be at least 3 integers between them. Okay, because if you can't find 3 integers between them, they're bound in between, you know, a couple of integers, and so they would be closer together than 3. Okay, now let n be the smallest number, the smallest integer. Okay, such that m times a is less than n. Okay, and so this is illustrated here in the picture. I have my little n is bigger than the na. Okay, and then I'm going to have an n plus 1 and an n plus 2 in there, and then I'm going to have an m times b. All right. Now, so m times a is less than n plus the square root of 2, because square root of 2 is less than 2, guys. We prove it. Okay. So it follows that a is less than n over m is less than n plus square root of 2 over m is less than b. Okay. Now, it's easy to see that a over m is a rational number. Okay. And it's just a little calculation to see that if n plus the square root of 2 over m were rational, then square root of 2 would be rational too, and we know that that's not the case because we proved it. Okay, so consequently it follows that a, b contains both rational and irrational numbers, and that's pretty cool. All right, this video has already gone on pretty long, and quite frankly YouTube might make me break it into 2 parts, but we have one more thing. I promised this is the last. Okay, if 0 is less than r is less than 1, then r to the nth power converges to 0. Okay, and so like if you have 0.999, if you take it to the nth power, each time it's getting a little bit smaller, well, ultimately it will be sucked down to 0. All right, that's the idea here. We're going to have to take some time to prove it. Okay, this is hard. Okay, given the point of the course we're in, this is hard, but I wanted you to see it. Okay, let epsilon greater than 0 be given. Okay, suppose that capital N is such that 1 over little n is less than epsilon, and now let's consider the reciprocal of r. Okay, which again we're taking the special case. Okay, we're starting out, and this is something that's done. We're proving things in special cases, and each time we're making the case a little less special. Okay, so here I'm taking a special case, p over p plus 1. So I would be saying like 9, if p were equal to 9, this is 9/10. Okay, or p equal to 999, this is 999 over 1,000. All right, but anyway, so we have r. Now we're going to flip that over. The reciprocal of r is p plus 1 over p. Now note that p plus 1 over p is equal to 1 plus 1 over p, again, to the nth power. Okay, I'm going to be taking these to the nth power. Now, I've broken it down like this because I want to expand it as a binomial. Okay, so when we expand something out as a binomial, I got, 1, and then I have n choose 1 times the second thing, right? 1 over p, plus n choose 2 times the second thing squared, and we keep going out like that till we get to the end. Okay, and depending on how big n is, this could be quite long, but this is the cool thing about analysis. A lot of times we get to quit worrying about equality and just worry about the inequality. Okay, so I don't know what the rest of these numbers add up to out here. I do know everything's positive, so if I throw them away, I know that this first line is at least as big as the second line, and I can calculate what the second line is. This is another, when you can actually know what something is exactly, that's pretty cool. So I know that 1 plus 1 over p to the nth power is bigger than 1 plus n over p. That's just true. Okay. Now, because all of the terms we drop between the first and the second line are positive, right? So we just know this. Okay. Now, suppose then that little n is bigger than capital N times p. Okay. Then 1 plus 1 over p to the nth power is bigger than 1 plus n over p, which is bigger than 1 plus n, which is bigger than n. So when I take the reciprocal of everything, I get p over p plus 1 to the nth power is less than 1 over n is less than epsilon. So by the squeeze principle, this r to the nth power converges to 0. Okay, pretty cool. End of case 1. Case 2. So for r, a rational number. Okay. Okay. For r, a rational number, we let r be equal to p over q for pq natural numbers, and we're going to have that p is less than q because r is less than 1. Okay. So since p and q are natural numbers, I know that q is at least as big as p plus 1. And so q over p minus p plus 1 over q is equal to, again, q minus p plus 1 over p, which is bigger than 0. Just I know that is the way it has to be. Okay. Now, therefore, q over p is bigger than or equal to p plus 1 over q. So p over q is less than p over p plus 1. Therefore, p over q to the nth is less than p over p plus 1 to the nth. Okay. And so since by our first case p over p plus 1 to the nth converges to 0, it will follow by the squeeze lemma that p over q to the nth will converge to 0. All right. Take that. All right. Finally, the last case, we have, say, r is a real number. Let us now consider a general real number with 0 less than r less than 1. There is a rational number p over q so that r is less than p over q is less than 1. So r to the nth is less than p over q to the nth. By the previous case, p over q to the n converges to 0. Therefore, by the squeeze lemma, r to the n converges to 0. And we are done.